I consist of 5 parts. Reservation research objective, number solution to KP1, rejection of number certain solution. You know, the KP equation is a very famous nonlinear equation. It can be modeled waves in plasma, paramagnetic media, shallow water, nonlinear optic media, photons and condensates. As we all know, as sigma squared equals to -1, we usually call it KP1 equation. While sigma squared equals to 1, we usually call the KP2 equation. This equation was first obtained by Prism in 1970. For KP1 equation, we all know it has localized solution we call the lump. It is localized in all directions, in y direction, x direction, and falling at xy minus 2. Such a solution was first discovered numerically in 1976. And the single and multi-lump solutions was obtained in 1977 and 1978. Then, symmetric stationary multi-lump solutions without free parameters and with free parameters was obtained by Kalinowski and Uris in 1993. And the Skew lump solutions was obtained by Wen-Cheng Hu in 2050. The Skew stationary multi-solutions was obtained by Uris in 2050. My topic mainly on the Skew lump solutions. Skew lump solutions we can travel with angle to x direction. And the interaction of single lump solutions is done in 2004 by Lu and Skew. And the result shows the interaction of solutions is elastic. They don't change their shift and velocity after the collision. Questions remain unknown about the lump solutions. How secure the structures depend on the free parameters of the stationary multi-lump solutions. Interaction of multi-lump solutions is not clear so far. It is similar with the single lump one. The aim of our work get a more general scale than stationary multi-lump solutions by filter method. And we analyze the detailed structures of the free parameters than the interaction of lumps numerically. Follow the work Professor Wen-Cheng Hu and Uris. We solve the KP1 equations by filter by linear method. First, we use traveling wave transformation where Vx and Vy are constant. Then KP1 equation is easy to convert to this equation. Use the transformation, it's easy to convert to this form where mu equals to minus Vy by quarter Vx, making filter and size, and substitute this equation into this equation. KP1 equation is easy to convert it to the bilinear form. A single lump solution, we take F as 2-degree polynomial of x and y with terminal parameters a2 to a6. Substitute f in this equation, here's this equation, solve this equation, we can get the parameters. Here we can see just have two free parameters, A4 and A5, and we get the lump solutions of the KT1. And test U is a stationary lump solution, and easily get the original variables. We also get the amplitude equal to 4 minus mu squared. The U is non-singularity when mu changes between plus and minus 2. In the original variables U, we also can get the magnitude, the triangle. When V1 equal to 0, it represents a symmetrical lump substance. When V1 not equal to 0, it represents a skew lump substance. Here is the same. When mu not equal to 0, it represents a skew lump substance. As you can see from the picture, when mu equal to 0, it represents a symmetrical lump substance, and it travels along x direction. When mu not equal to 0, it represents a skew lump substance and travel with angle to the x direction. In the same way, we can get three lump solutions. Take f as 6-degree polynomial of x and y with determined parameters A2 to A28. The substitution yields 66 equations for 27 parameters. So the equation, you get 4 parameters. Then you get the bi-lump substance when the 4 parameters and mu equal to 0. It represents a bi-lump substance which have two humps. And this case, the amplitude is the biggest one. And mu not equal to 0, it represents a skew lump substance. The one mu tends to minor and plus 2, the amplitude tends to 0. When the other parameters not equal to 0, we can get triangular, upper angular, triangular, also right left triangular and right triangular. When mu not equal to 0, we can get a skew triangular. And this picture is a scattering of three lumps with different parameter space, and it can be a line or a curve. Also, in the same way, we can get 6 lump solution with 12 degrees of polynomial, and this yields 2,276 equations for 90 parameters. So with 276 equations, we get 6 free parameters. And this is a 6 lump solution. When all the free parameters are equal to 0, we call this triple lump. As we can see, we have 3 humps. But we also can get triangular, up angular, triangular, left or right. We also can get the shape pentagram when 2 parameters are not equal to 0. We get the symmetrical pentagram or a symmetrical pentagram. and the mu, when mu not equal to 0, we get a skew lump substance. The next part is the interjection of lump substance. This part we use the finite difference. First, we examine the instability of the multi-lump substance. As we all know, for single lump substance it is stable, but the multi-lump substance we still don't know. As we can see from picture, with 5% noise of initial condition, the single lump substance keep it cheap, while the bilump substance or multi-lump substance is unstable. It's split into 3 lumps, and they also can interact with themselves. It's very interesting. Further, we look at the interaction of 2 single lump substances. We choose different initial velocity. Vx equal to 4.51. Then the interaction, we call this interaction the elliptic collision. The 2 lump substances separate in y direction, then come back. But in this case, they will not come back, and separate in y direction and go infinite. And this work is done by my teacher Lu and Grumshaw, and the maximum separation between in y direction depends on the initial relative velocity differences. The scale depends on the initial phase. Now we look at the oblique interaction of 2 single lump substances. There are also 2 cases: elliptic or inelliptic collision. It just depends the initial velocity, and the direction. And this is the amplitude before collision and after collision. And we can see the amplitude increase before interaction and decrease after interaction. So we can give argument. The interaction between lumps is attractive. Now we look at the interaction of bilump substances. We choose 2 cases with same velocity and different velocity, which is shown different from the single one. First case is inelliptic, and it's more complicated than the single one. It's not only interact with another multi-lump substance, but also interact with themselves. For the oblique interaction of 2 bilump substances, you can see at first the 2 bilump substances split into 3 single lumps, 3 lump substances, and we call this process is approximate elastic interaction. The direct interaction of 3 lump substances, we also choose same velocity and different velocity. All the case is inelliptic, which is different from the single one. Unfortunately, our conversation dominant is not so large enough, and the worker is underway. A breaker of 2-3 lamp solitons. In this case, it shows elliptic interaction. We also believe that with other directions or velocity, there should be elliptic collision. Some arguments. Interaction of single and multi-lamp solitons is attractive, no matter before or after the collision. Interaction of multi-lamp solitons is different from the interaction of single one. In the case, direct interaction is much easier becoming into elliptic. The component lamps of the multi-lamp solitons can also interact with themselves, by interacting with another multi-lamp, which causes the interaction more complicated. I should note that the result in the numerical part, our result is just qualitative, and the quantitative result is underway. Conclusion. Multi-lamp solitons with free parameters obtained by the filter bilinear method. Elliptic or inelliptic collisions not just depend on the initial velocity differences, but also the traveling directions for the interaction of single lamp solitons. Elliptic and inelliptic collisions depend on the initial relative velocity differences, traveling direction, the space, the distance of each component lamp solitons for the interaction of multi-lamp solitons. Thank you for your kind attention and patience.
I do have some questions. Firstly, how can you imagine you get three number and 6 number, right?
Yeah.
So how can you say you have such an example of polynomial just for the function A? From second order this is the number, right? And the second one
Six degree.
Yeah, why didn't try one put up the 5th degree or 4th degree?
This is
We just test it. I just test it because we have the first result, the test result. You just insert it. You don't try from.
I don't say this.
Or you have.
This is have been.
What is n here?
Verified.
What is n here? Check n.
N is a natural number.
Nature.
When natural number. 自然数 in Chinese 自然数。
It's an integer number. Okay. So you can n is
integer
the power of
number.
x.
N is an integer number. When
So n is the power of x, right?
M is M is the number of lamp.
Yeah, so that's an
M is the lamp. 2 times M.
Right. Clear. Okay.
Yeah.
So why then you don't try the second power, third power, fourth power of x, this kind of version? Why don't you try?
I have, but not get the lamp solution.
Okay, so this is very fun. Anyway, I have another question is more advanced anyway. So, the line solution was already classified by using Wen-Cheng. So, my question is, can you classify the lamp solution also by using some kind of determinant method, whether Wen-Cheng or some other Fredholm or some other determinant?
Determinant. answer to with polynomial. Determinant is very difficult for me.
The line solver classified by using this beautiful non-state. You take the linear combination for every element in the non-state, and then you can get all right solvers. Then you depend on the coefficient. You can classify all situations of the line solver for TT1. And the line solver, I think they are so similar about the classification. It's pretty dark. Anyway, that's probably you can go figure it.
Thank you very much.
Thank you.
Any more questions? Okay, thank you very much, Mr. Hu, for your presentation.
Thank you.
This is the end of this section. Then